Hey, I'm back and surprisingly not dead. This should be relatively interesting. So there's a company in China called PZEM that makes basically like, you've probably seen these in other videos, but they basically make plug-in energy monitors like this that use a little current transformer and gives you, volt amperage, actual wattage, power factor, and all the other relevant bits of useful information. And they've subsequently released a bunch of kind of slightly terrifying bits and bobs. For example, here's a standalone energy meter they released that basically is intended to be used with the computer. This one was kind of a bit of a trash fire. You can see the PZEM. So these are optos because the whole section on this half of over here is mains connected. So this is obviously because it's running off AC and it needs to measure the line voltage, large portions of the circuit is mains connected. But so that effectively means this plane is connected to one of the AC lines through a relatively low impedance, probably a resistor or two. And they ran it right over the opto isolator. So the copper pore went over this whole section here, including all of the isolated areas. So this was kind of my attempt to make it a little bit less of a will kill you. I haven't actually done much with this one, but it was pretty horrifying, very unsafe, but basically this is a off-the-shelf Chinese energy monitoring IC. It's actually relatively interesting. It's made by a company called SDIC, and it was functional if kind of lame. What they've now done is they now have these, which they slightly amusingly brand communications box, though they did in fact cost $10.29 each. These are standalone ones with a much better serial interface. So there's the actual unit, and then this one comes with a current transformer. So they have two variants of this. They have the model 14, PZEM 14, and PZEM 16. The 14 has a current shunt built in. It would be this one. Also, they ship it with a little USB dongle. So these are interesting because they had pictures. I saw something like on Alibaba of the internals, and it looked a little bit like they were slightly less it will kill you. They also have software for talking to them, which is interesting. So these attract me because they don't just give voltage and current, they actually give wattage and power factor and a lot of that other information that's kind of much more useful if you're looking for slightly more complicated monitoring. So this is the PZEM 14. This one's interesting because you can see the AC actually wraps through it, whereas this is the PZEM 16, which is interesting because it doesn't use, the AC doesn't wrap through it, the AC goes through a current transformer. A lot of different Chinese products use these. They seem relatively common and kind of cute. And then it actually also comes with a USB RS485 interface, which is this, which I think is probably just a CH340 and a transceiver chip. Yep. So there's very little in here. This is these are relatively common. I actually bought one of these myself for fiddling with my CNC VFD, because that also talks RS485. One thing that's really common with a lot of these really kind of low quality RS485 interfaces is what you see is they don't have a ground, it just has A and B. So they rely on returning the return current through the differential channels, which is kind of horrifying. But, what can you say? Yeah, so also on here is a, I don't know if you can see it, but yeah, it's a CH340. So CH340, for those who aren't familiar, is the it's a Chinese USB to serial converter. I actually kind of strongly suspect that the if you remember a while back, there was the issue with somebody in China selling knockoff FTDI devices that then got bricked by the FTDI drivers. I kind of suspect that those people just finally ponied up and got their own drivers done, because the CH340 is everywhere now. I wonder, it wouldn't surprise me if the internals of the two were the same, and what just happened is once they could no longer basically use someone else's VID, they finally just dealt with it and got their own. So this obviously has screw terminals. It's a little more proper. It actually has their logo on it, which is kind of cute. Yeah, so this one's 0 to 10 amps and this one's 0 to 100 amps. Interestingly enough, they both claim 1 milliamp resolution. So I'm not sure if they're just lying, bald-faced lying, or if they actually have similar resolutions on both of them. Yeah, so this is just really... I mean, I guess it's better to have mains electronics that snaps together too well rather than not well enough. Yeah, so here we are. So here's our main. So if we look on the bottom, we can see that presumably, well, okay, that would actually make sense, which is these two terminals are connected and these two terminals are connected. So, you know, mains comes in here, goes out here, comes in here, goes out here, which is actually interesting because that isn't compatible with how this one works, where through the edges. So the boards must be like actually fairly distinct. So the first thing you notice with both of these that I find interesting is they have actual switching power supplies. The transformer, the power supply, isn't a capacitive dropper, which is actually not that surprising when you realize that effectively, because this is intended to be used with the computer, and actually I think it can supply 5 volts at like 80 milliamps according to the specifications. Well, here, let's just look. So they give you a yeah. Current output capability is 100 milliamps. So they can power your shit off of their internal switch mode supply. So they give you 100 milliamps of 3.3 volts or 5 volts. So they'd have to have some sort of facility for, you know, providing a decent amount of power. That's way more than you can get out of a capacitive dropper like one of these, where you're, you know, maybe 5 or 10 milliamps without a whole lot of local dissipation. You know, basically in this case it's just enough to run the monitoring IC and nothing else. I think also RS-485 might be slightly more energy intensive. So here are the two units. Here's one, here's the other. First thing I notice is the circuit boards are actually distinct. So there's PZEM16 and PZEM14. They're both version 1.0, which is interesting. That makes sense when you consider the out N, in N, line out. That's actually fairly interesting because they don't specify neutral or line on the bottom side. I mean, I guess it really doesn't technically matter. That obviously must be their... Now that's 100 ohms, so that can't be their current shunt. That's the input filter. Goes through 100 ohms, through a series diode into the bulk bypass capacitor, 2.2 microfarads at 400 volts. And then we have a bunch of stuff. That must be, oh hey look, so this is their offline switcher, S9111AC. We obviously have power devices over here. Various, presumably for startup. There's the transformer. It's really adorable. Look how small that is. And over on this side we have a diode output, 470 mics, 16 volts. One thing I'm noticing is there's no post-regulation on the downstream side, and there's no opto. I don't see any opto, so they must be doing primary side sensing. Actually, we can see here that there's so this is the 5 volt out here, and it runs here. Here's your optos, and then this section here that's presumably the regulator for the 3.3 volt stuff, which if we look closely is a 7133-1. So presumably that tells us 3.3 volts. Little, it's not a 223, I forget what that package is. And we have here, this is a V9881. This is a V9881. I don't recognize that chip logo. I'm sure someone in the comments can elucidate. Other things of interest is if we look over here, we actually have ground, TDI, TMS, TCK, TDD, and mode. So this apparently has a JTAG interface for programming. It also says HSB 594.1. And then there's very little else on here, which is interesting. Particularly, I don't see, there's the switch mode converter with another logo I'm not familiar with, and then there is the 3.3 regulator. Over here we have a Max 485. I'd be really surprised if that's an actual Maxim part. Don't know what Q1 is. It might be another little linear regulator. So there's our opto in the two directions. There's just some capacitors over here. I don't see a resistor chain for the I don't see any resistor chains for the high voltage. Actually, one thing that we could do, and because I haven't found the current, we haven't seen the current shunt yet either, is I wonder if it's on the other side of the board. This okay, so there's the current shunt, 1 milliohm. Look at that, they actually bothered with Kelvin connections. That's nice. But oh hey, wow, so see, did anyone else see how silly that is? So here's your high voltage input, you know, presumably on these two pins, and then they have an isolation gap, and then these two pins are also high voltage. So that's your smallest isolation section. This is actually nice. They actually have, it's way better than this one, which had literally, the isolation on this one was literally whatever their copper pullback is. You can see here the solder mask ran right up to the safe pins. It's still pretty horrifying. You can see this is mains connected, so you still have that really small amount of clearance there, but they appear to have at least done something. So the worst clearance on this entire circuit board is this gap right here. It's not great, and they left flux in it, but it's a damn sight better than what they used to do. And for 120 volts, and considering I'm basically going to be running these on Wi-Fi, a little, probably like an ESP8266, I don't really care. It doesn't need to be perfectly isolated. Yeah, I don't see the divider chain for the 120 volt mains input. It must, yeah, I think I do. I think it's right there, because that's at 105. And if we look here, this is on, well, so the current shunt is right here, which means that they'd have to be probing these two pins somehow. So, and the whole thing is referred to, yeah, so it's treating, it's live ground, so effectively they're treating the live as the ground. So then that via there, so then this via here, and this via here would be your current input, and then this is your current input filtering, where you have series resistors, capacitors to ground, capacitor differentially, and then it goes differentially into the device. This thus must therefore be the series capacitor for the high voltage. But how is it connected? Let me just beep this out. So, yep. So if we go between that pin there, all right, so this pin here is tied to neutral, and if we go to ground, yep. So that resistor in series with, actually one thing we could probably do is I bet this is ground and this is ground, yeah. So we have resistor, capacitor, resistor, and there's between this point and this point is 160, 170 volts, whatever AC mains is. That's kind of how you do it. Yeah, like for the stuff I've done, when we did this, I had a chain of 5 resistors to spread the voltage drop across, because typically even like surface mount resistors like this are only rated for 100 volts in a lot of cases. Anyways, let's see, I should actually, I'm realizing you can put this into the housing backwards, because this is, I wanted to at least match how the sticker says it should go. So it's a little how you doing, but it's orders of magnitude better than the previous variant. Let's see, let's put the case I broke on the 14, because the 16, the two 16s are going to go right into a project I have. So this is relatively nice. The case is apparently bilaterally symmetric, so you can put it on this way or you can put it on this way. It's reversible. Or it's not. Watch me eat my words. It's not. So close. Yeah, see, this is much more proud than this section here, and actually this hole's smaller. Which makes some sense, because they recognize that, you know, this is going to have 10 amps going through it, and this is going to have maybe 10 milliamps. So it's asymmetric, which is nice. Interestingly enough, despite the fact that on this one there's not 10 amps going through this because it's intended to use a current transformer, they use the same connector. So yeah, looking closely at this one, it looks pretty goddamn identical. Yeah, so I think the only thing they changed is a little tiny bit of this routing. I think it's literally just the routing here that's different. Because you can see here, here's your current transformer input. They just moved this short from here to here and got rid of the shunt, pretty much. You can actually see, if you look closely, well here. Yeah, you can actually see that these two pins are tied together. And also they didn't clean the flux after they soldered it, which is typical. Other than that, the rest of the circuit is completely identical. Even down, yeah, so the same mains voltage divider, same exact thing. Hey look, so that must be, that's cute, 3.3 volts. Oh wow, 1.8. I wonder if this IC must have an internal voltage regulator, because how else would they get 1.8? That might be why they have several banks of caps. They actually have like 3 tantalums. That's like kind of impressive. Little 32 kilohertz watch crystal. Same switcher, same everything else. Oops, let's see. And then just because it's all apart, he says before being unable to get the housing off. Here's the USB to serial converter with the CH340, and then this also has a Max 485 and some very high quality soldering. But yeah, so it's kind of interesting. This is the only, I think it's the only USB to serial converter chip you can get that's in an SOIC rather than like a SSOP, which is what all the FTDI devices that are not like QFN or something obnoxious are. So it's a little interesting. There's actually a Q1, I wonder what that is. Yep, so just a couple parts, not much in here. Yep, so at this point it's time to put it in the thing I want to put it in. Hey, so it's about a week later. You may not be, actually 2 weeks later. You may not be able to tell, but I spent the last 2 weeks grappling with software. So this is, if I get the probes off of it, this is an ESP32, the ESP32 gateway from Olimex. I like it because it's got actual wired Ethernet, and this is actually the inside of one of the I didn't have any USB to, or serial to RS-485 converters, so I took one of the two of these I had and made my own. You can see I lifted off the, these are CH340, and I lifted off the CH340, which was here, and some of the control logic to drive the buffering, and the crystal, because why not? I wanted to see the traces under it. So this is now hooked up. You can actually see every time that light flashes, that's because the module is asserting the transmit line, so it's actually currently polling the power sensors on my computer. Most of the last 2 weeks was spent trying to make MicroPython functional. I wanted to use MicroPython because Python's cool and why not. Unfortunately, the port of MicroPython to the ESP32 is very broken. Well, it's still very broken. Primarily the support for the serial interface is limited to none. The ESP32 supports hardware RS-485 control, so it can, basically it has it can toggle RTS when, or CTS, one of the above, when it's trying to transmit, so effectively that controls your direction of the line driver, because again it's a half duplex bus, so you have to tell it whether to transmit or receive. But unfortunately, the version of their software, the IDF is what they call it, that supports bidirectional communications, was literally merged like about 3 weeks ago, maybe a month ago. Well, a little longer, early July. And the MicroPython is based on a much earlier version, or not much earlier, 2 months old. It's all very recent. 2-month-old version that didn't have those APIs, and they didn't expose them anyways. So I spent a bunch of time trying to figure out how that works, because the ESP people decided, oh, we're going to redesign how we handle partitioning data on the flash. So I spent a while trying to get that to work, didn't succeed. Then I moved on to just trying to use RS-232 and toggling the transmit-receive line manually, added a bunch of stuff, wound up running into issues with where the MicroPython has somehow got the baud rate generators in the ESP32 to the state where it can transmit or it can receive, but it can't do both. So if I transmit at 9600 baud, the serial coming out of the ESP32 looks correct. I've timed it on the oscilloscope, you saw the probes, but it doesn't receive, the receive data is garbled. If I receive on the ESP32, I have to receive at 10-250 baud, and it receives 9600 baud content perfectly, but if it transmits it at the wrong baud rate. And then if I send data to it with 2 stop bits from the PC, because I had the other one of these, they're actually wired together right now in bust along with the sensors. If I set the PC device to 2 stop bits, it seemed to work. But I double checked down through I actually wound up recompiling a bunch of custom versions of the IDF, and it's definitely set to 1 stop bit, but it's not working. And if I use the exact same settings outside of MicroPython, it works. So I have no idea what they're doing. It's very strange, and I wasn't able to understand it, and I spent a week or two fiddling with it, just in the evening in my spare time. And just, at this point, I'd much rather have a functional energy meter than a functional MicroPython, so I gave up, and 3 hours ago just wrote it all in C, and it took about 2 hours, and one of those hours was fixing some of the Modbus libraries I found, because they were kind of broken too. Open source code is garbage, including mine. So anyways, it's now reading, and the actual the actual devices, what have I? The PZEM 16s are currently installed in my closet. So it might be a little hard to see, but the 2 devices are down in here. They are currently connected. Oops. Up through those 2 connections here. So you can see them, they're right here. This is a fail-safe transfer switch with 2 mains inputs and a mains output, so I'm actually monitoring the 2 inputs. Right now it actually comes in, goes through the transfer switch, loops through my big UPS, which is that black box down at the bottom, comes back in and then goes out to my servers, which you may be able to see are right here. Sorry, this bright wing is a ring light I put on my camera just because it's dark. Yeah, so those are both installed and it can talk to the computer, and on the whole I've been relatively happy with them. All my problems have been related to software outside of it. Actually, that's not true. So the software they ship with these is hilariously bad. One of the features you can do, so you'll have to forgive me for filming the screen here, but the software they ship is this, Ningbo Peacefair Electronic Technology Company Limited. So the software they ship is kind of amusingly bad. First of all, it doesn't support COM ports higher than 12, which is problematic because on my computer I certainly have COM ports that go up to 26. I actually had to go into the device manager and reassign this. So right now it's on COM 22, but it fails because one of the things you can do, you can't even change that now. One of the parameters you can set is what is the Modbus ID. It defaults to 1. I set the 2 in the closet to 2 and 3 because they're on a bus. And it doesn't have any way to set the remote Modbus ID. So the software expects it to be on 1, and if it's not on 1, it fails, which is kind of ridiculous. You can't control, I can't do anything to it because it's trying to talk to the wrong port. So fortunately Modbus is relatively standard, so this is a little like Modbus testing application, and we can see here that if I try and talk to slave address 2, we get data, and this is 114.8 volts. I think it's 802.7 watts. If we look, the documentation's actually not bad. So you have current value low bits, current value high bits, current power value low bits, high, etc. So we have, you know, a fair bit of stuff. 98% power factor, 60 hertz, no alarms. I don't remember how this... I just wrote the software to parse it. I think this is saying 8 amps and 898 watts. Or it might be the other way. I think this is the wattage. No, this is power, so it's saying 930 watts. That's higher than I'd like, but not unreasonable. So this is apparently the... oh, this is watt hours? Oh, I think this is actually an accumulator that ramps up over time. Obviously, I've really only just gotten this working. So this is the little the script I wrote, where you can see that it basically outputs data from these. Actually, so if I go to 3, yeah, so you can see this is the side that doesn't have any load on it, because right now I don't have the power loop through the GPS, or the UPS, excuse me. If I go in and flip that switch in the transfer switch, it would then loop through it. Right now it'll switch over to the UPS when the power goes out, but it's not running it through the UPS, because the UPS I have is a double conversion. It's an always online one, and I haven't really, I wanted to be able to see how much power it's dissipating when it's running, so I've just hooked it up and haven't really done much with it. You can see here that it's saying it's currently drawing 0.5 watts, which I believe is the relays in the transfer switch. It's got a whole pile of relays in there. But yeah, so there's just, you know, relatively straightforward, lots of bit shifting and stuff. But it does, in fact, let me plug it in. I unplugged it because the two Modbus devices get cranky because they both want to use the same bus, and there's no real good arbitration. Where did it go? Oh, I closed it already. Yeah, so you can see here. So, yeah, voltage. I don't know why the voltage value is so different. I think these things aren't very well calibrated. What I'll actually do is I'll swap them and see. Sorry about the light. Yeah, so 907 watts. I'm not entirely certain what that is. Anyways, so I'm pretty happy. They seem to be reasonable little diddly bobs. One of the things I'd still like to do is take the internal shunt variant and put a 100 milliamp load on the 5-volt output and see how warm it actually gets. So I'll probably do that. You know, basically, I want to see, because one of the things I'd like to do is see if I can put an ESP8266 in this housing. Yeah, because there's plenty of space in this area here. So I don't see any reason I couldn't remove the cover, or remove this output terminal jack and like glue an ESP into the casing here. One thing of interest is that since it does indeed have the so both of these, the both the module and these USB to serial converters use automatic direction switching, which I think basically just means when you send when you're not sending a 0, it asserts the bus. I'm actually not entirely certain how it works properly, because from the amount of this I traced out while working on this, it appears that when you send a 0, it would deassert the bus, but it really needs to assert the bus negative. So I think there might be a very short time constant, like if there's a time constant that prevents the bus from being deasserted for, say, 2-bit times. Well, it'd have to be 8-bit times, because you could send all zeros. I'm not sure. It's weird. I haven't looked too closely. I haven't had really given enough of the shit. But in any event, these internally, the CH340, I believe, has CTS and DTS and all the control lines, but they're not connected. It just uses a transistor off of the TXD to switch the transmit receive on the RS-45 line driver. So I'm pretty certain this uses the same arrangement, because again, it only has 2 optos. So assuming there's RS-232 or 9600 baud serial data, not RS-232, going across these 2 optos, I bet we can just pick off here with a 9600 baud UART and get serial data. So, fucking ants. It's been hot here recently, so we've just had ants coming out of the freaking woodwork. But a lot of that is dependent on this thing being able to put out enough power to run an ESP8266. You know, can they squeeze by on 100 milliamps with high bursts? You know, so fun project, maybe to come. But on the whole, I think they're pretty cool little modules.